Okay, this video is going to have 3 parts in it, and that sounds like a lot, but the third part is kind of optional, and you could stop it after the second part if you really want to. I'm going to be going over some special factoring cases, and in order to get this video, you really need to understand greatest common factor and factoring trinomials and some of the other videos I would have done. Okay, so remember that when you're factoring, you want to always look for a GCF first. So that's just a little reminder, just something to hold on to as we go through any factoring questions. Now, right now, I'm not going to do a factoring question. I'm actually going to ask you to expand, just as a way of getting us started. And you'll see why in just a second. So we're going to expand this out, and hopefully you don't necessarily need to draw your arrows anymore as you do this. You may know how to do this using the FOIL method or just by multiplying everything out. So let's just multiply it all out, and I'm going to get x squared plus 4x, and then I'm going to get a minus 4x, or I guess depends on the order in which you do this. But just when I do it in my head, this is the order that I get it in. And then I'm going to have a minus 16 because 4 times 4 is 16, and a positive and a negative make negative. And we're going to hold on to this right here. This is important for what I'm going to be talking about later. What we notice here is that the 4 x's cancel each other out. I had a positive 4 times x, and I had a negative 4 times x, and now that's going to be 0. So let's take a look at what that looks like after we complete the statement and collect our like terms. We finish off with x squared minus 16. We end up with a binomial. And essentially what that means is that our x item has a 0. So that would be x squared plus nothing x minus 16. And we're going to explore how we can deal with this a little bit later to help us factor when there's only a binomial. Okay, the first special item or special case that I'll be doing is difference of squares. A difference of squares is a binomial with a subtraction sign between 2 perfect squares. A perfect square would be something like 4 because that came from 2 squared. So anytime you have something that came from something squared or is square rootable to get a whole number answer like 9 and 81, those are all perfect squares. And if I had a statement like this, 64x squared minus 81, I can take the square root of 64, that's 8. I can take the square root of x squared, that's x, and I can take the square root of 81. We're going to ignore the fact that it's negative for a second, and we're not going to worry about that when we take the square root. We're just going to say to ourselves, I know I can get 81 by multiplying 9 times 9. Let's take a look at something here. I've got a binomial x squared minus 64, and I've been asked to factor it. If we take a look at what I had done above, where after expanding I said that the 4's canceled each other out, and I ended up with a binomial. This is a difference of squares right here. The subtraction sign, and those are both perfect squares. What that amounts to is the fact that my x term had no coefficient or a coefficient of 0. And we have that again right here, x squared plus nothing x minus 64. And if we were going to do this the old school way as a trinomial, we would say to ourselves, I'm going to use product and sum. There's no greatest common factor. The a value is a 1, so this is what we call a monic trinomial. So I need 2 numbers that multiply to make negative 64 and add to nothing. The fact that it's a square rootable answer is very helpful because the factors of 64 that add to nothing, specifically negative 64, would be 8 and negative 8. And if we were to factor this using just product and sum, I would say that's x plus 8 and x minus 8. And that's it, it's factored. That means there's a pattern that we can follow here whenever we have a difference of 2 squares. What we did was we took the square root of the x squared, which gave me x, and x, because x times x is x squared, and I took the square root of 64, which gave me the 8. And the fact that the 64 is technically negative, in order to get a negative when we multiply, we have to have a positive and a negative. So it's not a true square root, but what we're doing is we're getting that root factor. Let's apply that to this second example that is no longer set up with the x squared as the first term, in this case m squared. We are going to try and factor 25 minus m squared. It's not a trinomial, there's no greatest common factor, but it is a difference of 2 values that are perfect squares. If I follow this pattern, what I need to do is take the square root of the first item, so the square root of 25. The square root of 25 is 5. That will be the first item in each bracket. And I'm going to take the square root of the second item. The square root of m squared is just m, nice and simple. In order for this to work out and multiply to a negative m squared, one has to be positive, one has to be negative. If you want to go ahead and just factor it using product and sum, you'll have to put a 0 in for your x. If I take a look at my original example that I had up there, I'll just do that in purple. If I had 64x squared minus 81 and I asked you to factor that, because I can take the square root of this, that's 8x, and I can take the square root of that, that's 9, I end up with 8x plus 9 and 8x minus 9, and I'm done. I'm factored. That's as factors as I can get. Let's take a look at two more examples of that. Pause the video and try them yourself. They're a little bit more complicated, I will admit. They're much more complicated what you saw up above. The hint being that the first one has a GCF. Did you give it a try? I hope that you did. Let's continue here. I've got a GCF that I can factor out. A 2 is factorable out of both, and so I'll factor out that 2. Always want to look for GCF first. Always, always, always. Just makes your life so much easier. And then I need to check and see if this is still factorable. It's not a trinomial. I can't use product and sum or anything like that, but it is a difference of squares. I can take the square root of these, that's xy, and I can take the square root of that, it's 5, and I will have a positive 1 and a negative 1 in order to meet that pattern. If you wanted to check your work, you could just expand it all back out. You should end up with the original question. Okay, try and apply that to the next example before I go ahead and do it. Pause the video and give it a shot on paper. Always look for a GCF first. Okay, there is a GCF. It's just 5, so I'm going to factor out a 5. That'll leave me with a to the power of 4 minus 81. All right, a to the power of 4 minus 81 does not look like a difference of squares, but in fact, I can take the square root of a to the power of 4. The square root of a to the power of 4 is a squared. With that in mind, I'm going to continue and actually factor this because it's a difference of squares. So that would be a squared plus 9 and a squared minus 9. And there, we've factored it. But have we factored it fully? This last binomial here is itself a difference of squares. Sometimes we have to go even further. So I had the GCF of 5, took it out. I ended up with a binomial that is a difference of squares. So I factored that out. That left me with another binomial on the end that is still factorable. That's a difference of squares. So a plus 3 and a minus 3. And that is as factored as that can get. Okay, that was the first special case, difference of squares. We're going to move on to the second one here, which is called a perfect square trinomial. We're going to start by expanding. So what we have here is a perfect square. Let's expand this out, and you might remember the pattern. Those of you that don't remember the pattern for expanding it out can go ahead, write the brackets twice, expand it out using your FOIL or what have you. But the pattern is to square the first, multiply the two terms and double it. So negative 5 times x is negative 5x. Double that, negative 10x. Probably went a little bit fast there. And then negative 5 squared. We're going to square the last term. And the last term squared is 25. And if you'd FOILed it out, collected your like terms, whatever, you'd end up with this as a trinomial. What we're going to do is we're going to try and use that pattern, that shortcut, to see if there's a really easy way to factor trinomials like this. What was the pattern? So if we have a binomial that is a plus b squared, when we expand that out, we are going to square the first term, multiply the two terms, so a times b, and double it, so 2 times ab, and square the last term. That's the pattern that I used to get this trinomial by expanding. What we want to look for is we want to look for trinomials that fit this pattern. Can I take the square root of the first term? Yes. Can I take the square root of the last term? Yes. And those square roots, in this case x and 5, if I multiply those and double it, can I get the middle term? Well, 5x times 2 is 10x. So yes, I can. And so that allows me to factor it. That may have gone over your head, so let's put it into practice. So we need to determine the values of k so that this trinomial is going to be a perfect square trinomial. So let's follow that pattern that I was talking about above. I can take the square root of the first term, that's x. I can take the square root of the last term, that's 5. If I multiply these, I get 5x. If I double my 5x, I get 10x, and that means that in this case, my k would have been 10. See if you can follow that exact same train of thought. Now, what I have here on the screen is just rough work, just sort of showing my thought pattern here, my thought process. See if you can follow that and get the k value over here. It's a little bit different though, because this k value is on the end. So pause the video, see if you can figure that out. Let's try and follow the pattern for this. We're going to take the square root of m squared and get m. And we're going to take the square root of k, but we don't know what that is. We know that when we take these two values, the square root of m and the square root of k, and we double it, we're supposed to get negative 20. Okay, negative 20. And specifically negative 20m. I'm going to divide both sides by 2, so that leaves me with m square root of k is negative 10m. I'm going to divide both sides by m, so that leaves me with the square root of k is negative 10. Well, if the square root of k was negative 10, which we can't get a negative answer when we take the square root, so let's ignore that for a second. If I square both sides by squaring here and squaring here, I will get that k is 100. All right, if k is 100, let's check this out. Let's see if this works. The pattern is to take the square root of the first term, that's just m, take the square root of the last term, square root of 100 is 10, and then whatever those multiply and double give me the middle here, which is negative 20. So that's great. How do I get negative 20? Well, this would need to be negative 10. So this would be m minus 10 times m minus 10. Let's go back to the first one now and factor it, because the question did say, and then factor. If I'm going to factor this, I could use decomposition, but the pattern is that I would have squared to get to this one. So that's going to leave me with x if I take the square root. I would have squared to get this one, so the square root of that is 5. And if I multiply 5 and x and double, I should get 10x, which is positive. And so I'm pretty sure this is x plus 5 squared. And the only reason why I didn't factor this to begin with is because it's the one that I had up here, just with x minus 5 instead of x plus 5. Definitely factoring perfect square trinomials is not only difficult to explain necessarily, aside from just memorization, but it's also difficult to put into practice. So let's try it again. I'd like you to pause the video and see if you can figure out how to factor this one using the pattern. And if you don't want to use the pattern, you don't have to. You can just factor this using product and sum or decomposition or what have you. Okay, I hope you tried it on your own, but I'm going to try it right now. So if I did this using product and sum, I would ask myself, what are the factors of 16 that add to make 8? And the answer is 4 and 4. So the shortcut, the really fast way, is to just say, okay, I can square root 16, that's a 4. I can square root x, it's just x, or x squared, it's x. And that leaves me with an x and a 4. If I multiply an x and a 4 and then double it, I get 8. And so this would be x plus 4 squared. Now, if we go back to doing it the product and sum way, just to compare, what I would have written is I would have written x plus 4 times x plus 4, which, as we can all see, is x plus 4 squared. And so it's just a shortcut here. Now, try the final example on your own, and the biggest hint that I can give you is to look for GCFs. All right, I'm feeling a little green here. Let's put some green down for this one. So I'm going to look for a GCF. What I see here is that they all have 3 in common, so I'm going to take a 3 out, and that will leave me with 4c squared minus 12c plus 9. And now I need to see if this trinomial is in fact factorable. If I was to do this the traditional way, I would do decomposition. Multiply my 4 times my 9, that's 36. Find the factors of 36 that add to 12. But is it a perfect square trinomial? Hint, hint, it's in this video. So yes, it's a perfect square trinomial. Let's use the pattern and check that pattern. Square root the first one, so that's 2c. I'm just going to put that up here, 2c. Square root the last one, so that's 3. Okay. If I multiply these, I get 6c. If I double that, do I get 12? Yes, I do. I get 12c. So again, square root the first, square root the last, multiply and double, you should get the middle term. And if you do, then that means it's a perfect square trinomial, and you can use the shortcut. The shortcut is the square roots of each, grab the sign of the middle term. If you hadn't caught on to that already, that's how we do that. That's how we determine, because I would have to get a negative 12, and that's what it is squared. Again, if you don't like that, you could easily just do this using decomposition, which is in my previous videos. You can totally check that out. Okay, that brings us to part 3 of the video, which is just more examples. So if you think you've got it, or if these are going to be maybe too difficult for you, pause the video or stop the video and move on to some practice work. But I would like to try these to see if we really understand what we just learned. So we're always going to look for a GCF. Pause the video, try this out for yourself, but the GCF is 3, so I'm going to take a 3 out, and that's going to leave me with 25 n to the power of 6 minus 1. And we've been asked to completely factor this, which is a huge hint that there's going to be more factoring to do. So I have a binomial. It is a subtraction in the middle, and I can take the square root of all of these values, the square root of 25, the square root of n to the power of 6, and the square root of 1. The square root of 1 is just 1. So I'll take the square root of 25, that's 5. Take the square root of n to the 6, that's n to the 3. I will take the square root of 1, which is just 1. And I will add and subtract that. And if I double check and multiply this all back out, I'll get back to my original. I'll check to see if it's factorable anymore, and it is not because I can't go any further. Let's try the next one, looking for a GCF. I don't see a GCF, but I have a binomial squared. My instincts tell me to expand that out, and I have another binomial squared here, and my instincts say to expand that out, but I have not been asked to expand. I've been asked to factor. What we really have is a difference of two things that are squared. This is a difference of squares, and so I can treat it like all of the other difference of squares questions. What I'm going to do is I'm going to have two brackets, one that is positive and one that is negative, just like I did in the other difference of squares questions. I'll take the square root of the first one, so that's 2a plus 5, and I'll take the square root of the last one, which is a minus 1. And these are technically package deals, but I don't really need the brackets because they didn't apply to anything. I'll do it again. So 2a plus 5 and a minus 1, but this is where putting this in brackets really matters because this I'm subtracting this bracket, and so this is a negative 1 outside here. And if you really understand algebra, you'll understand why that's important. Now I'll collect my like terms. This is 3a plus 4, and I'll collect my like terms here. So this is 2a minus an a, which leaves me with a single a, and a 5 minus a negative 1 means to add, so that's a 6, a plus 6. And that, believe it or not, is the factorization of this, and it's not factorable any further. Let's move on to two final examples. These are not binomials, which is a huge hint. Probably going to be perfect square trinomials because they're in this video, but let's just take a look. Pause the video, try them for yourself, but always look for a GCF. 4, 28, 49, those don't have anything in common. I do, however, have an A and a B in everything. So I'm going to take AB as my common factor. That'll leave me with 4a squared minus 28a plus 49. Okay, so that leaves me with a trinomial in the center here. And that trinomial looks like a perfect square. I've got a 4, easily squareable, or square rootable, I suppose, or rooted, and a 49, easily rooted. So that leaves me with, what's that? So the square root would be 2a, the square root here would be 7, and if I multiply a 2a times a 7, I get 14a. 14a doubled is 28, so in fact, this is a perfect square trinomial. So I can take their square roots, I will need a negative, and the square root of this is 7, and bam, I have factored this. Again, you could use decomposition to do it. It would just take you a little bit longer. And the final example in this marathon of a video, let's give this monster a try. This is just disgusting. Look at this thing. All right, we're going to look for a GCF. I have a GCF of 5. Well, that was very boring. None of the variables are coming out as GCFs. Okay, so 24x3, that's a 3. Believe it or not, y3. 720 divided by 5 is 144. So 144. My writing is getting sloppy, but that's okay. And now we're going to try to continue factoring this. Is it a perfect square trinomial? It's definitely not a difference of squares. Could we use decomposition to do this? I suppose technically, but the 6's and the 3's as those exponents is really starting to get to me. Can I take the square root of x to the power of 6? I can. It's x3. Can I take the square root of 144? Yes, that's 12. Can I take the square root of y to the 6? Yes, that's y to the 3. If I multiply and double these, I get 24x cubed y cubed. So this is a perfect square trinomial, and these are my two terms that are going to go in the brackets. It's positive because it's a positive 24, and I was able to successfully factor this monstrosity just using that perfect square trinomial factorization pattern, and it's beautiful. Okay, I hope you watched the whole video. Maybe you paused it or stopped it after a couple sections or what have you, but we're going to want to keep practicing our math. As with anything in life, it's the only way to get better. If this video went too fast or you didn't quite understand it, please check out other videos online. I highly recommend Khan Academy, and of course you could just YouTube search this thing up, perfect square trinomials and difference of squares, and keep learning math. Take care.